I want to thank all of you for coming out today, spending the next hour or so learning a little bit about MAXNET Energy. I think this is an incredibly exciting opportunity, and I mean that from many different perspectives. From the perspective of the science, I think that this partnership is going to accelerate what we're doing at the University of Virginia, but also is going to accelerate exciting research in some of the Max Planck Institutes. I think it's a great opportunity for the students, both graduate students, undergraduates, postdocs, research scientists who are going to be engaged in these projects. As I'll talk about, they will be collaborating with some of the world's leading scientists and with some of the most recognized research institutes globally. So it's an incredible professional development opportunity for these students and postdocs. I also think it's an incredible opportunity for the University of Virginia. What I'll describe today is the starting point for what I think is a very important area of research that I think will have great benefits. But I think this could be the seed of something much larger that results in a long-term partnership with several of the Max Planck Institutes that can have a benefit beyond the 4 or 5 year time frame that we're talking about today. I want to mention that I'm going to talk about these projects from a very high level. So from a high level, I mean from a viewpoint of what our broader goals and applications are. I will mention some of the science and some of the approaches we're taking, but I'm not going to wade down into the weeds too much. Certainly in a Q&A period, if anybody would like to talk a little bit more specifically about the science that we're working on and some of the challenges and opportunities, we can do that. So I want to start by telling you what MAXNET Energy is. MAXNET Energy is a new research cooperation, and the goal is to develop fundamental science in chemical energy conversion processes related to catalyst materials and different techniques that can be applied to solving problems. And this is one of the aspects that I really appreciate about the Max Planck Society and the way that they do their research. I like to call this use-inspired fundamental research. So we are an academic unit, and we are doing new science. And that gives us the freedom to explore, in some cases, new ideas that might be a little bit out there in terms of their potential, but that they could have dramatic impact if they're successful. But we always keep our eye on solving problems. And so I like this approach. It is a part of the culture of the Max Planck Society, and it's certainly going to be a part of our approach under MAXNET Energy. MAXNET Energy is currently comprised of 10 partners. There are 7 Max Planck Institutes, the Fritz Haber Institute in Berlin, and of course UVA, as well as Cardiff University. So University of Virginia is very pleased and proud to be one of 2 international partners that have been invited to participate in MAXNET Energy. There's an initial investment from the University of Virginia and the Max Planck Society of $4 million, $2 million on each side of the ocean to get these projects up and running. So there's a great commitment both locally as well as from the Max Planck Society and a great belief in the importance of the research that we're doing. I think one really important aspect of this is that it's a highly multidisciplinary effort. And so I'm a chemist. I am in the Department of Chemistry at UVA. This MAXNET Energy program is going to allow us to work with engineers, material scientists, computational chemists in ways that we wouldn't ordinarily be able to do and have the freedom to do. And it's really important to be able to pursue these projects in this fashion if we are actually moving towards solutions. And as I'll show in a few minutes, we're looking very much at some of the fundamental chemistry. But to understand how we might ultimately transition those chemical processes to a device or an application, it's really critical for us to be able to interact with the engineers, as much as sometimes I hate to admit that as a chemist. Okay, the groups that are currently heavily involved in MAXNET Energy are shown here. In addition to my group, Bob Davis from Chemical Engineering, Hossein Hajgariri from Mechanical and Aerospace Engineering, and Giovanni Zangari from Material Science and Engineering. I will mention that there are other research groups, both from chemistry and chemical engineering, who have areas of expertise and interest that could fit into MAXNET Energy. And it's one of our goals, ultimately, to expand the number of research groups here that are involved in this program. And so that's something we are already thinking about and seeking to explore. There are two primary areas of focus in terms of our broad goals under the MAXNET Energy umbrella. One is an area that's been of long-standing interest to myself and my research group, and that is the development of new processes for scaled utilization of natural gas. Now that might be a bit of a surprise because certainly this country, as well as globally, natural gas is already used as a primary energy resource. But I think it's being underutilized, and certainly there are cases where natural gas is being wasted with no net energy production from that. And there are solutions to that issue, and I'm going to talk about that. So this is something my group's been working on for quite some time, and I think there are great opportunities in this area. And there are reasons in terms of thinking about the environmental impact, in addition to thinking about just new energy production, as well as chemicals production, to think about this problem. Probably the major focus of MAXNET Energy is the development of new processes for scaled utilization of solar energy. And I'll talk a little bit broadly about why solar energy, and then what some of the opportunities are, and I'll funnel down into specifically under this category what we're focusing on MAXNET Energy, and tell you what our rationale and motivation for this is. I do want to give a little bit of background about the Max Planck Society. I know that a lot of you in the room are probably already familiar with the Max Planck Society, but there's an interesting history here that I think is in part important as to why the institution, University of Virginia, as well as the scientists, are very excited about this opportunity. The Max Planck Society actually was formed in the 1940s, but the root of the Max Planck Society goes all the way back to 1911. It was originally the Kaiser Wilhelm Society. It is probably, I put here, it's Germany's most recognized and acclaimed research organization. I think that internationally it is probably the world's most recognized research organization. The success over the decades of research from the Max Planck Society, I think, is unparalleled, and the talent and the expertise there is really quite exciting. There have been a total of 32 Nobel laureates come from the Max Planck Society. That is if you include the Nobel laureates that were part of the Kaiser Wilhelm Society. If you look at only the Max Planck Society, I think that number is 18, but it doesn't include those from before it was officially the Max Planck Society. There's actually an interesting history to the transition from the Kaiser Wilhelm Society to the Max Planck Society. This was after the Second World War. The Office of Military Government wanted to shut the Kaiser Wilhelm Society down. A lot of the scientists in that group had been involved in military science, all the way back to the First World War, the development of chemical warfare. One of the original institutes was the Institute for Coal Research, would look to making fuels both for domestic as well as for military purposes. And so some branches of the military wanted to completely shut this down following the Second World War. Some of the scientists in the Office of the Military Government recognized the incredible value, not to just Germany, but also to the globe, in keeping this incredible collection of talent and this very unique research institute together. And so they worked to make the case that the Max Planck Society, or in that case, at that time, the Kaiser Wilhelm Society, could be somewhat repurposed. And part of the political aspect of this was coming up with a new name. I think it was a physicist who was heavily involved in trying to make the case, suggested that the name Kaiser Wilhelm had a negative connotation for some of the Allies. And so as part of the repurposing plan, they changed the name to the Max Planck Society. And so I think in 1948, the Max Planck Society was officially born, but it came directly from the Kaiser Wilhelm Society. There are now 83 Max Planck Institutes, and they span very diverse fields across the natural sciences, life sciences, social sciences, and the humanities. The 7 institutes we're involved in, of course, are heavily seated in chemistry and engineering and material science. So I want to start in thinking about global production of energy. In 2012, the rate of global energy consumption was just under 18 terawatts. I've shown here a pie chart. This is from the EIA Annual Energy Review from 2008. There's probably been some modest changes since then, but nothing dramatic. This is the breakdown of where we produce energy, again in 2012, at just under 18 terawatts. As is well known, and is shown on this chart, of course, most of that energy is derived from fossil resources. The challenge here is that it's projected by 2050 that the rate of energy consumption is likely to be between 28 and 35 terawatts. This is a dramatic increase in the rate at which we need to produce energy. And to bridge this gap, if we want to do that without using fossil resources, is going to require a dramatic scale-up of alternative energy processes. And there are two reasons why we might want to avoid use of fossil resources to bridge that gap. One is, of course, the potential deleterious impact on the environment. But in addition to that, even if you're not concerned about the potential environmental impact of fossil resources, the incredible increase in demand for coal, petroleum, and natural gas that will result from this scale-up is going to really wreak havoc on the markets. We've seen a little bit of this a few years ago with the price of petroleum and crude oil going up and the impact on the price of gasoline. It's now come back down. That volatility will probably worsen and prices will continue to skyrocket. This will not only impact, of course, the energy sector, it'll impact the petrochemical sector and all the materials made from that. And so there's, I think, sufficient motivation, regardless of your viewpoint in terms of the impact of these resources on the environment, to try to develop alternative processes. A large part of the reason for this is because of the increasing industrialization of countries that have populations that are much larger than the United States. China is a prime example of this. In just 2000, China's energy consumption was about half of that of the United States. The rate of increase in energy and consumption in China is so substantial that in 2009, they passed the United States as the world's leading energy consumer. And it's projected to increase by 75% by 2035. That is just a tremendous rate of increase. And India is a little bit behind China, but that slope for India is also starting to scale up. And this is two of the primary reasons why the energy demand is going up. I mentioned that it's projected that we're going to need to produce energy at a rate of about 14 terawatts more than we do now by 2050, give or take. It's projected by the turn of the century, we will need to increase, that gap will be about 33 terawatts. And so coming pretty close to needing to triple the rate of energy production in what really is a very short period of time. Now the good news is there's no shortage of energy available to us. I've shown here some sources of energy. There are other possibilities. And the numbers shown here are estimates in terms of the maximum energy that we can pull from these resources. So if you want to scale up hydroelectric power by building dams on rivers, for example, it's estimated that the maximum energy rate of production would be about 4.5 terawatts. Now, I should point out this is a maximum theoretical. We would likely never get close to this actual number. In fact, if you look at the amount of energy produced from hydroelectric, we're not doing too bad here in terms of what's available and what's being produced. Biomass is another area that's been widely discussed as a possible solution to this energy gap. And while I think biomass can play an important role, and especially in certain environments a really important role, it cannot be the long-term solution to these large energy gaps. If you take all of the world's cultivatable land, that's everywhere you can grow crops, and what we know about the efficiency with which enzymes take sunlight and CO2 and store that in chemicals, it's estimated that the maximum rate of energy production would be about 5 to 7 terawatts. And again, this is an ideal number and the maximum efficiency that's possible. And so while biomass can play a role in certain areas, and certainly can be an important part of this portfolio, it cannot be the long-term solution. In fact, if you want to dramatically scale up energy production from non-fossil resources, there really is only one option that you can look at without some dramatic change in technology, and that is the use of sunlight. We get about 10 to the 5th terawatts from the sun. In fact, more energy from the sun strikes the Earth in a single hour than is consumed in the entire year from the entire globe. It is a tremendous amount of energy, and it provides far, far more than we need. There are two primary issues from a broad perspective to making use of this resource. One of those are the technologies to capture the photons from the sun and convert that into a usable form. And the second is how to store that captured energy. The sun goes down at night, certain areas of the globe, the sun shines with greater intensity than other areas. And so how we store that energy is also an important aspect to realizing this goal. In terms of conversion of sunlight, I've put here 3 different examples of how this might be done. One is basically to use sun as a heat source, as solar thermal energy. You could take mirrors, for example, and concentrate the heat from the sun, and then use that in various ways to store that energy. And there are some reasons to consider this. In some ways, it's conceptually very, very simple. But there are also some great limitations to this, and I won't go into the details of this. A part of it is the capital expenses that are required to build these solar thermal energy banks. Another way to do this, which probably has received the most publicity, is photovoltaics. So a photovoltaic, when it's struck by sunlight, will create electricity. And there are challenges with photovoltaics, but the good news is we can do this with reasonable success right now. You can buy solar panels and put them on your home and use that to power your home, for example. It still has the issue with how we're going to store that energy, generate electricity as long as the sun's shining. When it's cloudy, the efficiency of that electricity production goes down. Of course, at night, it goes away. Another way to conceivably do this is to develop photocatalysts. So this is in the realm of chemistry. And basically, and I'll have more to say about this in just a moment, what a photocatalyst does is when the sun hits that material, it energizes it, puts it in an excited state, and then it allows it to do chemistry that could then store that in a chemical bond. So a lot of people have given the moniker to photocatalyst artificial photosynthesis. And so, as is well appreciated, photosynthesis, of course, is the process by which plants convert sunlight, carbon dioxide, and water to stored chemical energy. And we'd like to be able to do the same. We'd like to be able to take sunlight in, use a photocatalyst, take water and CO2, and store that as an energy source, or perhaps just water. And I've shown here one example of how this might work. I've taken this from Harry Gray, who's a chemist at Caltech. He is involved in an NSF center called Powering the Planet, and they're trying to overcome technological and scientific challenges to making photocatalysts a reality. And the way this would work in one manifestation is the photocatalyst would take sunlight, here denoted by this symbol, and water, and split the water into its constituent elements. Hydrogen, in this case, is the fuel. Now, you can use hydrogen directly, or you can convert to hydrogen and, say, carbon dioxide to another fuel source, such as methanol, or even to gasoline. So there are other strategies. So I show hydrogen here as the initial fuel that's produced from this reaction. It doesn't necessarily need to be the end energy carrier. There are a lot of issues in terms of making hydrogen and using it, because it's a gas, it's explosive, there's some dangers with that. And so there's some real inhibitions in terms of the infrastructure to use hydrogen. But once you have the hydrogen, you can convert it to something else. This really is the important aspect of this overall process. And so what happens with a photocatalyst, you have essentially 2 different sides of this catalyst. You have water that comes in, sunlight strikes this catalyst and puts it in that excited state, puts it in a high energy state, and it allows it to do chemistry. And the chemistry that this photocatalyst would do would be to take the water molecule, 2 of them, each water molecule has 2 hydrogen atoms and an oxygen atom, and make oxygen from that. This is what we call the oxidation reaction. Now each water molecule has 2 protons, those are the hydrogen atoms, the H's, oxygen, and 8 total electrons. Water molecules are really very simple. That's what it is. Oxygen, 2 hydrogen atoms, and 8 total electrons. What this catalyst does is it takes, on this side, the sunlight, and it provides the energy to split water into oxygen. And when that happens, what we have left over are 4 protons, 4 H+, and 4 electrons. So we've stripped from 2 water molecules protons and electrons. Those protons and electrons move through a membrane, and then on the other side, there's a second catalyst that takes those protons and electrons and produces hydrogen. And so the way this would work is somewhere in Arizona, you would have a giant reactor with photocatalyst in it. That catalyst would be in water. The sunlight would hit the catalyst and Oxygen would bubble out from one side, hydrogen would bubble out from the other side. And you capture the hydrogen, the oxygen we don't care about. Let it go into the atmosphere. Now there are many advantages. I've shown here actually, this is a photocatalyst that was developed at Argonne National Lab based on cobalt. And you can see if you look closely, there are bubbles here. This is being hit with light. And those bubbles are actually hydrogen being produced in this photocatalyst. So this is the good news is this is science that we can do. It's chemistry we can do. But there are dramatic limitations to this approach. One is that the science isn't quite there. The catalysts aren't fast enough. They're very short-lived, those that are efficient. They break down very quickly. And so there's a lot of science and technology that needs to be developed to make this potentially practical. But there are inherent limitations to this that I think will limit application even if we ever overcome that science and technology. One is that your fuel has to be produced somewhere where there's a lot of intense sun. So you limit where you produce your fuel to somewhere like the southwest of the United States. But if you want to produce that hydrogen, say, in the northeast, where the sun's less intense, more cloudy days, you're going to have great limitations there in terms of the amount of fuel you can produce. So there's a real practical limitation to developing photocatalysts. You have to put those catalysts where the sunlight is the most intense. And so engineers would look at that and say, okay, this is a possibility, but let's see if we can devise a better approach to this. And this is the approach that I think from a scale-up standpoint, now I'm ignoring the science and technology, I think this is a more practical approach to this problem. And this is essentially the approach that we're working on under MAXNET Energy. And what I like about this is it uses existing technology and it couples it with the need for new advancements. And so in this approach, what we would do is we would set up photovoltaics, and you could put those anywhere you wanted, say in the southwest of the United States, anywhere where there's a lot of sun. And those photovoltaics would generate electricity, and then we could transport that electricity using existing infrastructure in most cases, maybe building some new power lines. And then you could take that electricity to where you wanted to produce the fuel. And then at that site, you would use that electricity to drive the chemical reaction. So rather than having a photocatalyst that requires sunlight, we would design what are called electrocatalysts. And those electrocatalysts would use that electricity. That's the energy that we generate from the sun, the usable forms of the electricity. And that would drive a chemical reaction using the electrocatalyst that would essentially do the same water splitting reaction. And so as an example, if you want to scale this reaction up, you're going to need a huge source of water. So you might like to build these reactors on the coast where you have access to a tremendous amount, of course, of seawater from the ocean. And that would make the most practical sense, I think. And so the idea here also that I like is it decouples two technologies. It decouples the conversion of the sunlight to a usable form with the production of the fuel. We can produce the electricity where it's optimal, and then we can take that electricity and do the chemistry where that's optimal. You might want to produce the fuel close to the site of use, for example. Now the other thing that I like about this, and I won't touch on this too much, is how that energy is being stored. There are multiple ways to consider storage of that energy. One that has received a lot of research and a lot of publicity, of course, is in batteries. And I think that batteries can have a dramatic impact. And I think there's a lot of really exciting research in that field. But right now, there are great limitations to scale up of batteries. One is if you want to use them in the transportation sector, it requires an entire change in infrastructure. You have to build up a fleet of vehicles that have batteries. You have to build up recharging stations. There are limits in terms of the materials that go into batteries currently. There are some questions about whether or not, for example, we have enough lithium to scale this up. And even if we do have enough, once you start to use the lithium, will the price skyrocket, and therefore then it becomes not economically viable. So there are all of these issues. They perhaps can be overcome with scientific advancements. So I think this is an important area of research. But when I look at this process, what I like about it is the product we're making is a product that can potentially fit into the existing infrastructure, meaning that if you take that hydrogen and you use that hydrogen to react with carbon dioxide and make methanol, that is a fuel we can currently use, the technology's there. And if you don't want to use methanol as a fuel, you can convert that to gasoline. That's known technology that was developed in the 80s largely. And so this process is potentially viable to take sunlight and essentially make gasoline or some other liquid fuel. And from the perspective of implementation, if this is successful, you can implement that much faster than if you try to, for example, run on batteries and you need the infrastructure for that. And so I like that perspective. Now, I want to be honest here, there are major challenges here. The good news is we can do every step here that we need to realize this goal, but there are major limitations right now. There are limitations in terms of the efficiency and the cost of photovoltaics. There are major issues with the efficiency with which we move electricity, major energy losses. And as I'm going to talk about in just a minute, I think the major challenge here is actually with the chemistry of this reaction. It's not what you do with hydrogen after you make it. It's the production of hydrogen from water splitting. And ironically, it's not the hydrogen production that's the issue. Now, I want to take a step back, and I want to be a bit idealistic right now. The other thing I like about this strategy is that potentially the impact can be much broader than production of fuels or energy. Right now, the materials that the chemical industry makes that are used for agricultural products, that are used for pharmaceuticals and medicines, really every facet of modern society, are predominantly produced from fossil resources. So we take hydrocarbons out of the ground, do oxidation chemistry, make new materials that are useful to society. It is possible in the future, if you can overcome the challenges of capturing that sunlight and developing electrocatalysts that have the stability and the efficiency to convert protons and electrons and feedstocks, that we not only can make fuels, but we could put nitrogen into those reactors and generate ammonia. That's one of the world's largest chemical reactions. That's fertilizer. So rather than making ammonia from natural gas, which is our hydrogen source now, that hydrogen could come from water, and we could use N2 directly to make that ammonia. You could take carbon dioxide and make many of the materials potentially that we make from fossil resources, etc. And so I do think there's opportunities here to impact just beyond fuels production. The issue here is that we need major advancements in the science and technology for this to be viable. You cannot implement this scenario just based on policy. You need major advancements, or we need major advancements in the science and technology. And the area that we're focusing on in MAXNET Energy is what I think, despite all of the hurdles, is the major inhibition to realizing this goal. And that is the oxidation reaction. If you remember when I talked about the photocatalyst, there are two sides to water splitting. The first side is you take the water molecules and you make oxygen. The second side is you take protons and electrons and you make hydrogen from that. Now, both of these reactions, in terms of the catalysts and the materials we use to do them, need new advancements. But it's the hydrogen production that we're farthest along with. The catalysts are very fast. They're stable to the conditions under which the reaction is run. The catalyst that we are really far behind is the water oxidation reaction. And this is ironic because we are not going to use the oxygen. It's not a fuel. We're just going to release that, but you cannot realize this goal without producing the oxygen. And you might ask, well, why even produce oxygen? And the answer is these oxygen atoms are in the reaction. And if you don't make oxygen, they stick to your catalyst and it kills your catalyst. And so we have to find a way to make this reaction much more efficient. And we are so far from realizing this goal. I think it is a bigger challenge than photovoltaics, than transmission of electricity more efficiently, definitely than hydrogen production. It is a tremendous challenge for the chemists to design new catalyst technologies that will do this reaction fast. Keep in mind, if you have a fuel production site, a reasonably sized fuel production site will produce about 100,000 barrel equivalents of oil every day. These catalysts have to be really, really fast to make this amount of material. And so we need much, much faster catalysts, but we also need these catalysts to be long-lived. If the catalyst deactivates every 2 or 3 hours, like most of the materials we have, it's just not going to be feasible. You can't shut down your reactor and replace the catalyst every couple of hours. These must run for at least months at a time. So I'll talk a little bit about the research that is being fired up at UVA in collaboration with some of the Max Planck Institutes under MAXNET Energy. This is Giovanni Zangari from Materials Science, And Giovanni's group has been working with some advanced materials that are based on titanium. They're making titanium dioxide nanotubes, and it turns out that this material is efficient as an electrocatalyst, both for the proton hydrogen production, but also for water oxidation reaction. And so Giovanni's group is working with these nanotubes, and they're going to be collaborating amongst other groups with the Meyerhofer group, who's at the Max Planck Institute for Iron Research. Now the value to Giovanni's group in the UVA, Giovanni's group is incredibly skilled at making these materials, and they can test their catalysis as well. But at the Meyerhofer group, they have designed a high throughput test, and they can test a larger number of catalysts much faster than we can. We don't have the instrumentation and the resources to do that. They can probably test a series of catalysts in 1 week and look at their efficiency in what would take us a couple of months to test. So this collaboration, the Giovanni's and Gary group is going to make these new advanced materials, and they're going to use their understanding of these materials to try to improve them. And then we'll send them off to Germany to be tested and learn what their efficacy is. And that's going to accelerate the progress of research. Yen Zhu is a first-year graduate student in Giovanni's group who's working on this project. Yen's right back here. So if you have questions later about this project and exactly what Yen is doing, you can grab him after my presentation. He can fill you in on the details. My group is actually doing a few different things in this project. We work with single molecules, so we don't work with the materials and heterogeneous catalysts. What we'd like to be able to do, a lot of the materials that are used for these catalysts are based on really expensive, what we call precious metals, platinum and rhodium. And there's two problems with using those materials. One is they're really expensive, and the other is we don't have many of them. So there's not a lot of rhodium available in the world, and if you want to scale up fuel production on a huge global scale, you're going to skyrocket the price of rhodium, and that's going to bring down the economic viability, and you may run out of rhodium. So we want to be able to do this reaction with less expensive materials. And so the types of things we'll be doing, again working with the Meyerhofer group, is we'll be designing molecular iron complexes. So you don't need to worry about what all this other stuff is, just focus here on the Fe, which is the iron. And we'll be sending those to the Meyerhofer group, and they're going to put them under oxidative conditions, and we'll be generating new types of iron materials based on what we design as the precursor, and then determining the efficacy of those complexes. And so I've shown this precursor here because based on what we understand about this chemistry, we think this is going to give a material that's going to be a great water oxidation catalyst. And what we can do very quickly is make dozens of variations of this starting motif. What we can't do quickly is put it under the reaction conditions and look at the efficacy. And again, that's where the Iron Research Group and the Meyerhofer Group is going to come into play. There are other things that we're going to work on, for example, with the Mullen Group, which is at the Max Planck Institute for Polymer Research, where we are going to take molecular precursors again, and we're going to make advanced nanoparticles from them. So they have some really exciting techniques where they use pyrolysis. These are high temperature techniques, and they make new nanomaterials from that. And so their advancements in terms of the features of the nanomaterials and our ability to modulate the molecular precursors, I've shown here some cobalt examples that they've actually used, will again allow us to make new materials that previously we can't make, and that the Mullen Group cannot make without our input in terms of making the small molecules. Okay, Hussein's group is also involved in this, and this is actually a very different approach to this. And it's something that I'm learning more about, and I think it's a really interesting application. And this is where MAXNET Energy can bring together scientific and engineering groups to do things that haven't been done before in a new way. When we first started talking about MAXNET Energy, this project was nowhere on the radar screen. And as we were looking at the science at UVA and looking at the science in Germany, it was recognized that there might be a good fit here. So the innovation of this technology originally had nothing to do with energy and fuel production, but we think there are potential applications here. And so Hussein's group has designed a new thermal management system, and our idea is to use this to help control solar thermal energy, to use that heat to drive chemical reactions to make fuel. The research scientist working on this is Mehdi Sadat, and he is here today. And I'm going to allow Betty to take just a second because I have very little expertise in this area. And these devices are really cool. And maybe he can tell a little bit about the history of this and then what is evolving with MAXNET Energy.
Yeah, sure. I mean, I actually have a little presentation. I'll just talk right without any presentation or anything.
Yes,
yes, basically, one of the, as Brent mentioned a couple of minutes ago, one of the big challenges of actually solar panels is that if it's flat, we actually have a very little efficiency converting solar to electricity. But the solution to that is that you have to concentrate solar lights, right? So once you concentrate that, then you can increase the efficiency of solar panels to 30%. Now it's still high. Then if there is a limit to that concentration. Once you go beyond that limit, then you're going to produce a lot of heat. And that heat is going to damage the material and everything else. So Hossen's group come to the picture in a sense that we're trying to design a device that actually dissipates that heat and uses it for producing energy in other resources. So the idea behind this device is evaporation. Basically, evaporation is a very efficient way of dissipating heat from a heat source to somewhere else without increasing the temperature. So think about it as if you have a solar panel, if the sun is actually concentrated on the solar panel, then what happens is that you can actually have a cooling device right here, which is dissipating the heat without letting the temperature of the device to go up. And that is the whole idea behind this device. I can talk about the details of it. Maybe at the end of the meeting, someone is interested. But the big picture is this: a device based on evaporation and using microchannels to dissipate heat from a heat source with little increase in temperature.
Thanks very much. Sure. So as I mentioned, this was a project that was nowhere on our radar screen when we started the discussions with the Max Planck Society. And it evolved out of that discussion. So one of the other exciting aspects of the MAXNET umbrella is that it's bringing groups at UVA together in ways that we hadn't worked together previously. For example, we have a new project that we are going to start with Giovanni's group. They're using their titanium nanotubes for water oxidation. As I'll mention in just a minute, we are interested in hydrocarbon oxidation for natural gas conversion. And so we're going to start a new collaboration with Giovanni's group using some of their titanium nanotubes for that. And so with that, I want to switch gears. So essentially in MAXNET Energy, under the solar energy, the primary focus is going to be that water oxidation reaction. New materials, new understanding, and new catalysts for that process, because that, we believe, is the major limitation right now in realizing this goal of taking photovoltaics and producing liquid fuels like methanol or gasoline. Now I'm going to switch gear and I want to talk about natural gas. And this is something that is beginning to receive some publicity in this country, but I think not nearly enough. I directed recently a Department of Energy EFRC that was focused on new catalysts for natural gas. And one of the striking aspects of that, there was a 5-year window on that. When we wrote the original proposal for that, the price of natural gas was extremely high, and there was a lot of concern over that. And so in our proposal, we made the case that because of the high price of natural gas, there was a great need for new technologies to increase the efficiency with which we use them. In the time span from when we were funded for that program and its 5-year window, it was a huge change. The price of natural gas plummeted. So here is a plot. This was actually from a couple of years ago, showing per year the price of gasoline versus natural gas. And if you look here, they're going in the opposite direction. So the price of gasoline until recently was going up, and the price of natural gas was going down dramatically. And so you might look at that and think, well, there's no need now to develop new technologies for it. It's so cheap. But the problem is, one of the reasons the price has come down is new drilling technologies have allowed us to access vast amounts of new natural gas. And some of the places where we've accessed this are in remote locations. And so in this country, we now have an absolute glut of natural gas. Now the challenge there is that the infrastructure to make use of that natural gas, especially in remote locations, is extremely expensive. And so while the supply of natural gas has changed dramatically, demand cannot change rapidly because we don't have the infrastructure in place to do that. One of the things that would be fantastic for this country is if we could take that excess natural gas and use it in the transportation sector. But to do that, you have to have vehicles that run on compressed natural gas. You have to have fueling stations, and you have to move that natural gas to those fueling stations. That is trillions of dollars of infrastructure. It's viable, it can be done, but it can't be done quickly, and there's an incredible expense to that. The other limitation here is investment in that infrastructure because of the volatility in the prices of crude oil and natural gas. Most companies don't want to take the risk and invest in that infrastructure. The price of crude oil comes down like it has recently, and natural gas goes back up, and then companies lose money. And so that's a real inhibition. Another outcome of this is flaring. This has been a problem on a global scale for decades, in particular in areas like Africa where they don't have an infrastructure to move natural gas around, and never have had. Basically what natural gas flaring is exactly what it sounds like. They light the natural gas on fire and burn it off. Produces carbon dioxide, get no use out of that. We don't make chemicals from that, we don't get energy output from that. This has become an issue in our country, and in particular in North Dakota. So in North Dakota, in the Bakken oil fields, they're currently extracting quite a bit of petroleum. They're also simultaneously accessing quite a bit of natural gas. But there's no infrastructure to move that natural gas, and so they're flaring it. This is a satellite image of the Midwest from probably a year ago, maybe 2 years ago. If you had looked at this image from about 10 years ago, you would have seen the lights from Minneapolis and some of the other larger, smaller metropolitan areas. But this area here, which is in North Dakota, where the Bakken oil fields are, that would have been mostly dark. And that bright light, of course, is not metropolitan areas in North Dakota. Those are natural gas flares. And they are flaring at a tremendous rate. It's currently estimated that there's about $100 million in value of natural gas that's burned off in North Dakota each and every month. Now, I should mention, I think that value is using the price of natural gas in Japan. If you change that for the United States price, that's about $30 to $35 million. And this has been escalating. Now, recently there's been a lot of publicity on this, and there's increasing pressure for companies to trap that. But the bottom line here is that it's economically better for these companies to light it on fire and burn it than it is to capture it and transport it and use it, because the infrastructure is so expensive. The solution to this is to design or develop a technology that you can take the light alkenes, methane, ethane, and propane from natural gas, and convert that to a liquid fuel. The reason this is so expensive is because it is difficult to take the light alkenes from natural gas and compress that into a small volume, a liquid ideally, and then move that. The pipelines to move natural gas around are very expensive. The liquefaction facilities to do that are very expensive. And this is primarily an issue with methane, which is anywhere from 70 to 90% of the natural gas. Propane, which is a much smaller component, is much easier to compress, and this is why propane is compressed and moved around and sold outside of the areas where it's tapped into. There is a technology that can accomplish this. You can take methane, which is CH4, and undergo what's called a steam reforming reaction. That makes a mixture of carbon monoxide and hydrogen. That's known as synthesis gas. And then the second step, that synthesis gas can be converted to methanol. Methanol is a liquid like ethanol is. It can be blended with gasoline just like ethanol can. Our gasoline right now is about 10% blended with ethanol. You can do that with methanol. Flex fuel vehicles that burn pure methanol cost about $300 more than the current engines that burn gasoline. So you can easily develop a vehicle fleet that runs on pure methanol or 85% methanol. More importantly, methanol can be converted to gasoline. It can be converted to diesel. Methanol is an incredibly versatile molecule. It's a liquid. It's inexpensive to transport. It can be converted to diesel fuel. It can be converted to gasoline. It can also be converted easily to precursors to make plastics, agricultural products, pharmaceuticals, etc. And so if we can do this reaction, then you can go to a place like North Dakota and build reactors, and you take that natural gas that's expensive to transport, and on site you just make methanol from it, and then you transport that methanol. Well, I've shown here that we can do this, and this is actually a fairly efficient process. The problem is the conditions for this reaction are extreme. And And so the capital investment in the plants is tremendous. These plants are very expensive. And so you can't go to North Dakota and build 200 of these syngas plants. The capital investment will kill you, and the companies won't make money. So we need a new technology that does the same overall reaction, but at more ambient conditions, and this would be the solution to this problem. A single catalyst that makes methanol from air and methane would solve this problem, would allow a very rapid scale up in the utilization. Just to show you some numbers to put an exclamation point on the expense, I've been following this story about a possible pipeline to Alaska's North Slope. This story for me started with Sarah Palin's acceptance speech for the vice presidential nomination. In that speech, she mentioned working with the Alaska legislature to work with the TransCanada Corporation to develop this pipeline. I think at that point the Alaska legislature was putting in like $50 million or something into this proposal. So I went and looked it up. At that time it was estimated these pipelines, there were two being pursued, were going to cost about $25 billion. I'm sorry, the seed money was $500 billion. I said $50 billion. Over the next couple of years, as I followed this, there were stories. The pipeline has still not been built, if you're wondering. The estimates of the price ballooned up to about $40 billion. The latest article I've seen, I don't think this is really being seriously discussed anymore. The estimate of that pipeline is $65 billion. So the expense is incredible. There's also, of course, public opposition to building these pipelines, as we well know in the state of Virginia. There's a proposal to build a pipeline from Harrison County, West Virginia, through Virginia down to North Carolina, and there's incredible public opposition to that. So there are real challenges, both economically as well as with the public, to scaling up this type of infrastructure. Now, here's an example of a syngas plant. It's estimated that Nigeria loses about $3 billion a year to natural gas flare. That's a tremendous loss to that country. Chevron and Sasol went in and built a syngas plant in Nigeria so that they could take some of that natural gas and make methanol from it, and other fuels as well. This plant is anticipated to produce about 33,000 barrel equivalents of oil per day. That sounds like a lot. The consumption in the United States is about 19 million barrels per day. So this is, a drop in the bucket, but still a reasonably sized plant. The original estimate for this plant was $3 billion. It ended up running close to $9 billion to build this plant. And that's a tremendous exclamation point because, and I should be careful, I take these numbers from what I read, and I'm not an expert in this area. This is the purview of the engineers. A conventional refinery, the investment in building a petroleum refinery, generally runs about $50,000 per barrel produced per day. It's estimated that GTL plants, that's gas to liquid, that's a syngas plant, has to be about $100,000 per barrel per day to be competitive when oil's at $100 a barrel and natural gas is at $4 per thousand cubic feet. This plant this is a different plant. This is a plant that's been proposed in Louisiana, would run about $140,000 per barrel. The Chevron Sasol plant is well above that. It's about $250K per barrel in capital investment. It's going to take years and years for Chevron and Sasol to make money from that plant. And they may never make money from it, depending on what happens with oil prices and natural gas prices. And so the main point here is companies are largely unwilling to invest in this because it's hard for them to make money. So this is what we want to do. We want to take alkanes from natural gas, air, and we want to design a process that runs at about 200 degrees. That's about 600 to 700 degrees below the syngas process. Make alcohols that can be used for fuels, chemicals, and also in fuel cells. Okay, so here's one example of what we're doing, and you can ignore all the language up here. This is a very an oversimplification of what we're doing, but this is our design strategy. We're going to have a catalyst that can break the bonds, the CH bonds of the alkane. So if this is methane, this is a CH4 unit, and our catalyst will break that CH bond, and we know how to do that. Organometallic chemists have been breaking CH bonds for decades. So the chemistry is here to do that. And then we want to take that complex that now has a metal carbon bond with methane, and we want to take oxygen from air, we want to make a CO bond. And when we do that, we essentially produce methanol. On paper, this is a really, really simple chemical reaction. The problem is the types of complexes, metals that I use, that do the CH bond breaking reaction. And the properties of the metals that form the CO bonds are entirely different. They couldn't be more different. And so it's a real challenge to figure out how to do this in a single reactor and to do it efficiently. And so we have a new approach to this where we're going to take nanomaterials that's made from the Davis group, and we're going to design a molecular catalyst. The nanomaterial will do one part of this. Our molecular catalyst will do the other part. And we'll design a tandem catalysis for this. And this actually came out of a discovery we made from a few years ago that was a very fundamental pursuit where we accidentally learned that these nanomaterials could do this reaction. We stumbled onto this. And it opens up an entire new area of pursuit that we're really excited about. Now, this is an example of what I'm talking about, fundamental research. We've got a lot of work to do, and this may not work. There may be issues that we don't have the foresight to recognize. But it's a dramatically new approach to this that I think has merit, and we've got proof of concept that it's potentially viable. We are also working with the Davis group now to design heterogeneous systems that have two types of metals in it. One metal will have the properties that break the CH bonds, and the other metal has the properties that will form the CO bonds. So we're trying to make a single catalyst based on what we learn and know from our chemistry that will then be a viable catalyst for scale-up. And so Gordon Brzezicki is a second-year graduate student in Bob's group that's working on this project. Gordon's right here. And Gordon's so enthralled with this, he didn't finish his apple, I noticed.
Thought it might be loud crunchy on it.
And so Gordon's actually doing a couple of different things. He's working on the bimetallic catalyst that I mentioned, and that will be in close collaboration with us as they design materials and we learn how they may or may not work. We'll then take the knowledge that my group has developed and tweak those catalysts that Gordon's making. He's also working with two students from my group on the combined nanomaterial molecular catalyst approach. We can barely spell nanomaterials in my group, so Gordon and the Davis group are going to make and characterize those new materials. We will make the molecular systems, and jointly we'll pursue this project. So I have two students in my group that are working in this area. One is Zhang Wen, who's a first-year graduate student. He's over here. And Zhang Wen is actually testing this reaction currently using hydrogen as a model for the methane. Hydrogen is easier to do chemistry with, so it's going to accelerate the pace of the research. And this chemistry is working so far. That's the good news. And so he's going to be designing the molecular complexes that are used to break those, form those CO bonds. Ali Verlander is another first-year student in my group over here that's working on this project. Raise your hand a little higher, Ali. Okay, so I've got two brand new, extremely bright first-year students that are starting up on this project. And Ali's doing something a little bit different that we also think is very exciting. She'll be working on this combined approach, but she's making materials that are known as porous organic polymers. So one of the problems with our molecular catalysts is they just decompose too fast. And that has to do with the chemistry of them, and so we don't need to talk about that. But we can design very, very fast catalysts for these reactions. But we put them in a reactor, and in 30 minutes they're dead. So that's no good. And so Ali's taking an approach where they're making these porous organic polymers, and the Davis group is helping us to understand and characterize these materials. And then she's going to put our well-defined molecular systems on those, what we call POPs, and that should stabilize those materials. It's going to prevent reactions that occur with our molecular systems. We've got proof of concept that this can work. We're now, with another process and another reaction, we're now trying to apply this to conversion of natural gas to liquid fuels. Okay, with that, I'll just conclude with a few points. I mentioned early on that I think the value of this new initiative with Max Planck is, well, there are several values of this. One is the science, and hopefully I gave you a sense of what we're going to be doing with new science and how the partnership with MAXNET can help accelerate what we're doing at the University of Virginia. There's also great value in terms of the professional development of the students. All of the students, research scientists that I talked about today, will be going to Germany to do science there and to collaborate with those groups. They'll be attending meetings. They will be using the internet to discuss research. And they're going to be working with some of the world's leading scientists and engineers on this. And so their advice and the mentorship they get, the scientific input, will be expanded beyond my group or Bob Davis or Giovanni or Jose's group. So it's going to really accelerate their advancement. We have complementary expertise in this collaboration. What they have in Germany, we don't have here, and vice versa. And so that's very exciting to us, and allows also for us to potentially recruit talent on a global scale in terms of graduate students, postdocs, new faculty into the effort as well. You can read the rest of this. I won't go through it. I'll stop there, and I'll be happy to answer any questions or try to answer any questions that you might have about MAXNET Energy, what we're doing, the science that's involved, etc.
What's the time frame with what you have laid out now?
So the initial project period for the MAXNET consortium is a 5-year period. What I anticipate, any new collaboration takes a while to get up and running. We all speak different languages, and there are many advantages to the collaboration with MAXNET Energy. The Atlantic Ocean is a big disadvantage, and so it's really nice to be able to go and walk across the hall to something. So what I anticipate is we probably will have about a 2-year time frame to get these new projects really ramped up so that they're humming along, we're doing new science, we're making progress. And then after that initial period, we'll see, I think, the real advancements. So from my perspective, what I'd like to see is that initial 2-year period, these initial projects will be up and running at an accelerated pace, and then we'll begin to try to fold in new efforts across UVA with MAXNET Energy. So it's a 5-year window for the initial process. Now, your question wasn't how long can we solve these problems? Okay. I have an answer for that, but it might not be as honest.
I will ask.
I love your presentation and the new stuff that's going on. But the beginning of this is the photovoltaic technology. Are you going to need, will the industry need new technologies in that area to produce enough energy, not only to replenish the materials that you're using to produce the energy, but to have enough left over that you'll be able to, feed the rest of the world?
Yeah.
Or is our current technology capable of producing that?
No, we need new advancements in every step of the process. So, from my viewpoint, photovoltaics, there's a limitation there. And so, absolutely, to realize this, we need more efficient photovoltaics and cheaper photovoltaics. That's an important component of this. The transmission of electricity is an area where I wouldn't say we need advancements to make this work, but it certainly would be beneficial. There's a lot of energy loss in that transmission using this strategy. So that's an area where I don't think there's a current inherent limitation. From the chemistry, of course, I've talked a lot about that, what the limitations are. There is another major issue, which I think we are farther along. When I say we, I don't work in this area, I mean the engineering scientific community. If you produce hydrogen, and you want to avoid new infrastructure, you don't want to use hydrogen fuel cells. You have to convert that hydrogen to methanol or gasoline. And to do that, you need a carbon source. Of course, that has to be CO2. So you have to capture that CO2 and concentrate it. And so right now, we're worried about 400 ppm levels of CO2. That's not a lot of CO2 when you're building a reactor and you're trying to make 100,000 barrels per day. It's possible, theoretically, to do that. But the materials to capture that CO2 and then to get it into a reactor, there's a lot of work that needs to be done there. And there's an energy balance, right? Anything that captures the CO2, it's going to capture it because there's an energy gain there. So you're going to have to put energy in to get it back out. So if there's too much energy gain from that CO2 capture, your net energy gain is not going to be in your favor. And if it's too little, it doesn't capture CO2 very well. So that's a huge challenge too, which I didn't touch upon at all. But this is part of my motivation also to work with natural gas. I think solar energy, we must solve these problems. But this is not likely to happen in 10 years, not on a large scale.
How did this get started? What was the initiating force for the MAXNET process?
Would you like to take this? So this is a long story, and I may have actually forgotten some of the details. It was in large part some unusual and unpredictable circumstances. So when I was directing the EFRC on natural gas, I was invited to an event at Darden where Robert Hefner was brought in. Robert basically is in the natural gas area, and he has moved to Charlottesville, and he and his wife own a vineyard here. And he wanted to talk about new drilling technologies, realities, some of the potential issues, the opportunities. And so, Robert was going to talk about the economic opportunities as well as the energy opportunities with fracking that were evolving at the time. This was all relatively new at this point. And so they wanted someone to come in and talk about the science of natural gas and what were some of the new technologies that could be exciting in this field. So I came in and talked about what we were doing in the center. About a week later, I was put in contact with Hans Gunnoe, who has an interest in energy. And Heinz wanted to learn more about what we were doing. Heinz's family is from Germany. In fact, Deb, correct me if I'm wrong, his grandfather was an attorney to Kaiser Wilhelm. So there's a link there. And so Heinz's family has a link to the Max Planck Society to Germany. He was excited about some of the things we were doing and thought that we might be able to work with the Max Planck Society. He put us in touch with people. We flew over and met with Peter Bruce, the president of the Max Planck Society, Robert Schlogel, director of the Chemical Energy Conversion Center, who was the leader of MAXNET. It turns out that Robert Schlogel had a collaboration with Bob Davis, and so there was a connection there, and it sort of all came out of it. And I should say, much thanks and gratitude to Deb, who led a lot of this effort and pulled all the important people together. Deb Donnelly was here, and actually was the catalyst to make all this happen. I'm glad you caught me. My students were rolling their eyes.
Are there any other questions? All right, well, thank you so much. That was really fascinating.
Thank you. Thanks to all of you.